Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove. You know, there are a number of theories that have now been put forward to unify consciousness with the latest developments in theoretical physics. And today we're going to explore several of these theories and we'll be comparing them. With me is one of my oldest and dearest friends, Saul-Paul Sirag, who is the author of ADEX Theory, how the ADE Coxeter graphs unify mathematics and physics. Saul-Paul himself has originated a model of consciousness that was originally published in the 1987 edition of my book, The Roots of Consciousness. This interview is being conducted via the internet, and now I'll switch over to that channel. Welcome, Saul-Paul. It's a pleasure to be with you once again. It's been quite a few weeks since we've had a video conversation together. I'm looking forward to exploring the different theoretical physical theories of consciousness with you. And I suppose a good place to start, it's always a good starting point as the insight that John von Neumann had back in the 1930s, that the famous collapse of the wave function in quantum physics is actually caused by consciousness.
Yes, that was a very startling result from John von Neumann's John von Neumann's famous book, Mathematical Foundations of Quantum Mechanics. At the time and later, of course, von Neumann was a very renowned mathematician, but he was very adept with mathematics and could understand the physics of quantum mechanics very clearly. And he showed that the so-called collapse of the wave function doesn't necessarily happen when one makes a quantum measurement with a piece of laboratory equipment, which is, of course, typically how we do it. What he showed was that the laboratory equipment itself must obey the laws of quantum mechanics, and that there would be a perfectly good Schrödinger wave equation that describes the functioning of the piece of equipment, which prior to the 30s, prior to von Neumann's book, it was assumed that the original Copenhagen interpretation of Niels Bohr and Heisenberg and so on, they were assuming that there was kind of a duplex world of that we were stuck with. That's, say, the quantum realm of atoms and subatomic particles was one thing, but the measuring equipment would have to be described classically. And von Neumann showed that was basically an assumption that they were making that was not really valid from the point of view of the pure mathematics of the Schrödinger wave equation itself. And moreover, the so-called collapse of the wave function, in other words, when a measurement is made, the idea in the Copenhagen interpretation is that the wave function collapses from a state of total indecision, just possibility of what the measurement might be, to an actual measurement, an actual measurement of the particle is here rather than there, so to speak, if that's what one is measuring.
In other words, the Schrödinger wave function is a probability function. It represents a range of possible outcomes, and the collapse of the wave function is when you observe one actual outcome. And von Neumann is suggesting that Schrödinger's wave equation can apply to macro objects as well as quantum physical objects.
Yes, and the macro object, say, of the measurement equipment would itself contain as a substructure mathematically the wave function of the thing that's being measured. But the measuring instrument itself would have a more encompassing wave function, and he also pointed out famously that there's no natural place for the chain of things to occur. Like, for instance, so you have a piece of equipment making a measurement, but you have, say, a human being who is looking at the output of the machine, and so there would be a wave function covering that situation, and so that would go back to the brain of the observer, and ultimately, he said, to the consciousness of the observer. And the consciousness of the observer is the only natural place for the wave function to ultimately really collapse. Nobody did anything much with that idea, I would say, until the 70s, when people like Henry Stapp and Evan Harris Walker picked up on that idea and proposed specific models of brain functioning where consciousness, mind, in other words, would actually play a role in for Henry Stapp at Lawrence Berkeley Laboratory. He emphasizes the idea of calcium ions in that function in the neurons themselves, in making the vesicle open up see, the vesicles in neurons contain the neurotransmitters that go out into the gap, the synaptic gap that's between one neuron and another neuron. And so for Stapp, that's the magical entry point for consciousness. Mm-hmm. And there are other people have other ideas of where this is, but some idea like that probably works. But to test that idea, it might be very difficult, actually. So there are many rival ideas. There's a handful of them that we could discuss maybe on this occasion, but there are probably 7 or 8 different approaches to physics and consciousness that are actively being pursued to this day.
Well, let me step back, actually, because whether it's calcium ions or Evan Harris Walker's idea that it's the synaptic gap itself, or any other idea, you still have the problem of coordination there amongst various neurons. And as I understand it, in quantum theory, every individual instance of the collapse of the wave function has a randomness associated with it. It cannot be coordinated. In order for consciousness to occur across tens of thousands or maybe millions of neurons, in any meaningful way, there needs to be some sort of coordination, doesn't there?
Yes, there needs to be coordination, and some people have suggested that that's where entanglement comes in as a coordinating tool, so to speak. If there's entanglement, if there's entanglement between these quantum events occurring at one neuron as opposed to another neuron, they could be entangled together. In Walker's model, it's as if there's another layer of connection in the brain, not just there's the ordinary layer that we all know about, which is the neurons and their synapses. But besides that, in Walker's model, there's an underlying, much more extensive electron connections between things, and it has to do with electron tunneling. But in order for this electron tunneling not just to occur at synaptic clefts, he introduces I guess what he calls hopping functions between certain macromolecules. I don't know how that idea could be tested, but it's an interesting idea. And he brings in a chain reaction. That's the word I want.
Yeah.
He's actually Evan Harris Walker. For his day job, worked at an Army military base, actually, as an expert on
ballistics,
on bombs, actually, nuclear explosions, and so it would be natural for him to think in terms of nuclear chain reaction. He introduces an equation based on nuclear chain reaction actually into his theory. So in other words, he makes it's more than an analogy. It's a very close analogy between a nuclear chain reaction going critical and the brain going into a consciousness state. In other words, that's another aspect of consciousness theory that has to be explained. What's the difference between a brain being conscious and unconscious? What's the difference? What is happening to make consciousness occur? And for him, it's totally analogous to a nuclear chain reaction going critical. That's a very interesting idea, of course. I don't know exactly how it could be tested, but that's he's written about that extensively over the years.
Let's contrast that for a moment with Stapp's notion of the calcium ions inside of the neurons, or at the synaptic cleft in the Bhutan, I suppose.
Yeah. Stapp has also written a whole book, at least one, on his theory, and so there's quite a bit of detail to it, but which is very different from Walker's idea. First of all, because he's using a quantum entity that's very different from Walker is using electrons as the quantum entities, which are much smaller than an electron. Mass is much smaller than that of a calcium ion, say, and so their theories are based on different levels of mass structure to start with, and so in that sense they're rivals to each other, but underlying both of those theories is the von Neumann idea of consciousness collapsing the wave function. and answer to the question, well, how does it happen in the brain? Is what they're trying to answer. Also, Stapp has introduced some ideas from philosophy, especially the philosophy of Alfred North Whitehead, and sometimes he calls it a Whiteheadian approach to quantum mechanics. In fact, he wrote a paper with a title very close to that. In other words, Stapp is more philosophically oriented, I'd say, and also Stapp also wants to make clear that his model entails something very important, which is free will, and that's I think a large part of his motivation for his approach to quantum theory of consciousness is to make free will a viable scientific entity, because many physicists, including quantum physicists, don't believe in free will. If you're in the classical world entirely, then everything is deterministic and there's no free will. But quantum mechanics suggested to many people, like way back in the 30s and earlier, Eddington emphasized free will as an aspect of quantum theory that is provided for by the uncertainty principle, actually, as what Eddington emphasized. And Stapp follows up somewhat on that, but in much more detail, I'd say, because of von Neumann's work and all the work that's been done since then. It's very important for Stapp to emphasize the free will aspect of quantum theory of mind. And I agree that that's an exceedingly important aspect of the picture.
Well, it seems to me that Walker also addresses that issue, because if I remember properly, when Walker is talking about quantum tunneling of electrons across the synaptic cleft, he did some calculations as to how frequently that could occur. And I seem to recall, at one time, at least, I had this notion that Walker's theory would permit a measure of free will in a human being, but that a great deal of human behavior would not, there wouldn't be enough quantum uncertainty in the synaptic cleft to allow for very much free will.
Yeah, well, Walker does emphasize free will also, of course, but in a somewhat different way. Then, of course, his model is radically different from Stapp's model of brain functioning at the quantum level. Mm-hmm. But yeah, Walker is very intent on free will and very opposed to determinism, one might say. And he has decried determinism many times. Walker also is very much involved in the parapsychology aspect of quantum mechanics, and famously used his theory to model the dice experiments of Forwald. Yeah. It's a PK effect on falling dice that Forwald, I think in Sweden or Norway, anyway, somewhere there. This was, known to parapsychologists, but Walker took on the task of using his model to explain how that PK actually works. So that's very interesting. Mm-hmm. I don't know of any other parapsychology experiment that has been modeled in quite that way. I mean, I don't know that Walker took on any other. The thing about the four-wall dice experiment is you had very, very specific parameters to deal with. It's a very simple system. You just have falling dice and see if some person who claims to be able to do PK can affect the outcome of the dice. And apparently it was an experiment with a positive result, not an overwhelmingly positive result, but strong enough so that it was statistically significant, certainly. And so Walker took that on, since it was a very simple system to try to model with his theory. And Walker also came up with what he calls the information rate that that his model allows, the information rate that the brain is using, but his information rate is fairly high, like I think 1,000 bits per second, and that's quite a bit higher than the usual claims that the information rate is much smaller than that, like maybe about 30 bits per second.
Are you talking about in the brain or in
the brain? Yeah, the information rate allowable by synaptic interactions, I guess, is what it amounts to. It may be that this much higher information rate is due to this. Remember, I mentioned this sort of secondary underlying system in the brain in Walker's model, not just the synaptic.
But is that the information for a single neuron, isn't it? 30 bits or 1,000 bits a second?
Yeah, between neurons, yeah.
That's across one synaptic cleft, and there are billions of them in the brain.
Yeah, that's right. Mm-hmm. That's right. Yeah, so it's not the overall information thing. Yeah, it's right. I'm glad you clarified that, what we're talking about, actually. Yeah. So that's why it's kind of low, maybe. Mm-hmm. Like 30 bits per second seems kind of low.
But if you combine all of the synapses, and again, you still have the problem of coordinating.
Yeah. Mm-hmm. Well, see, Walker gets his 1,000 bits per second out of his nuclear model. Actually, his
chain
reaction model. See, he gets. That's where he gets the 1,000, is out of those kind of equations. So that suggests that he's really talking about not the ordinary synaptic cleft information rate, but the information rate of this underlying system that he invokes in his theory. Actually,
I see. It's
very different from what Stapp is doing. But they both go back to von Neumann.
And I presume they both would equate free will with quantum randomness, how much quantum randomness is taking place in the brain, which is a macro structure.
That's correct. That's absolutely correct. Yeah, it's quantum randomness that allows, as far as they're concerned, the free will to occur, but it can only occur if the mind has some way of pulling out of randomness something actually happening, something actually being observed.
Like Maxwell's demon or something.
It's almost like Maxwell's demon, yeah. Mm-hmm. Which is a thermodynamic idea, yeah.
And your model is along the same lines. It's based on the von Neumann chain.
Yes, my model is based on the von Neumann chain, but it involves a lot of other, very different ideas than Walker and Stapp are working on, because it entails hyperspace. In fact, the title of my paper is a hyperspace view of quantum mechanics. Not of quantum mechanics, of consciousness, hyperspace view of consciousness. That's the title of the paper. And so I go into the hyperspace aspect of superstring theory, actually, and the consequences of that,
we've talked about it in a different interview. Let me ask you a different question. Let's bring in Penrose for a moment and okay. His model. How does Penrose's model differ from Walker and Stapp's?
Well, it's radically different in the sense that Penrose is again trying to answer the question of the collapse of the wave function, of course. How does the wave function collapse? Why does it collapse? Is the way Penrose would put it, I suppose. And what he claims is that it's actually gravity that collapses the wave function. When, in other words, if you have something that's the right amount of mass, that mass itself will affect the curvature of space-time in such a way that there will be a collapse of the wave function. But there are problems with that model. But Penrose has partnered in various papers with Stuart Hameroff, and Stuart Hameroff has another idea of consciousness in the brain, and that's a very different kind of model from either Stapp or Walker, and that has to do with the
microtubules,
the microtubule structure in the neurons, and that's a very intriguing. That structure is very intriguing, but I don't really see. I think his idea could stand alone without Penrose's idea at all. But he has combined his idea in some way with Penrose's idea. But I don't think it's really necessary. I think Hameroff's idea could stand on its own feet, so to speak. He's a very interesting guy. He got interested in consciousness because he's an MD who specializes in
anesthesiology.
He's an anesthesiologist, and of course, an anesthesiologist deals with the whole aspect of consciousness on a daily basis. What does it mean, and why? And a question for them is, why do these very simple drugs make a person unconscious, for instance? And that's something he's puzzled about his whole life. In fact, I believe that he actually went into anesthesiology because of his interest in consciousness.
Yeah, I think so.
Yeah. His ideas about the microtubules is very interesting because certainly that's at a level where quantum mechanics should function.
Well, how do the microtubules compare in size, do you know, as compared to the synaptic cleft?
Oh, I think they're smaller, actually. Yeah. I think they're the right size to be thinking about quantum effects. Sure. Which is, of course, why he takes that route,
Yeah.
So, and of course, these three very different approaches to the brain ultimately all in their own way depend on the background idea of von Neumann, after all. And given the fact that there are these three very different approaches to where consciousness arises in the brain suggests that there may be others. I mean, that these aren't the only three possibilities, I'm sure.
Right. So to recap, we've got Stapp talking about calcium ions, which I think are involved in the transmission of neural spikes along a neuron.
That's right.
Walker is talking about electron tunneling across the synaptic cleft, and Penrose is describing gravitational effects that take place in the microtubules.
That's correct. Yeah.
Uh-huh.
Yeah.
Now, and your model doesn't really address the brain itself, because you're really looking at activity that takes place in hyperspace, or what Hameroff sometimes calls the quantum geometry.
Yeah. Well, the thing is that ultimately one can think of interaction that particle interactions are sort of the bottom floor of quantum theory, of quantum the quantum phenomena.
Yeah.
And one can think of every particle interaction as having, you might say, an internal view and an external view. The internal view of the particle interactions, is a little blip of consciousness. In other words, any time there's a particle interaction, there's a little blip of consciousness associated with it.
Are you referring to a qualia, a moment of experience?
Yes, and the structure of quantum theory itself suggests that the ultimate qualia are what in quantum mechanics are called eigenvalues. You see, a set of eigenvalues is associated with every quantum state. Every particle has a particular set of eigenvalues associated with that particle, and to my way of thinking, those eigenvalues are the ultimate qualia of which, our experience of the world is a much richer collection of these primitive qualia, and the mathematics of the qualia is very suggestive of that, because the qualia actually are points in things that are called mirrors. Actually, that's how the mirrors come into the picture that I've talked about, the kaleidoscopic mirrors,
which are structures in hyperspace, in effect.
They're
mathematical structures.
The mirrors themselves are hyperdimensional in a hyperdimensional space. Yeah, and each dimension is associated with the qualia, actually, in each dimension of the mirror. To really make sense out of all that, you'd have to have a lot of diagrams, actually, such as I have in my paper that I published. I have a lot of diagrams in there.
Let me ask you this question, because as I recall from the diagrams, in fact, your model is fundamentally a dualist model.
Yes, it's fun. It's a dualist model in the sense that there are two types of space. There's ordinary space, and there's what you might call mental space. Mm-hmm. Yeah,
You talk about a universal consciousness, but you don't claim that all matter exists within a unbounded consciousness, which is what an idealist like Bernardo Kastrup, whom I interviewed this morning, would have said. That's correct.
Yeah. Now, in that paper, I point out that this dualist model has to do with overlaps between certain very specific algebraic structures, and from the point of view of the full set of structures, it's unified. It's monistic, let's say, because you have a single structure, but that single structure has substructures, which have a dualist aspect to them.
I mean, some people might call that substance dualism. Now, there's a unifying structure out of which emerges mind substance and matter substance, something of that.
That would be that. Yeah, I guess so. I'm not particularly familiar with that term, but what you're describing seems to describe what I'm talking about. Yes.
I mean,
substance dualism.
Yeah, I've heard of substance dualism, and I've heard of the term epistemic dualism, which is two different. We have knowledge of the physical world and knowledge of a separate mental world, but ultimately, at some deeper level, they're unified.
Yeah. Mm-hmm.
That they're not really separate. We just think of them as separate.
Right. Yeah. Anyway, so in other words, I'm proposing a very specific mathematical structure. I'm not dealing
with the brain. You're not really addressing
with the brain itself. I'm dealing with something much more primitive than that, which is the interactions of the particles themselves. Is the ultimate thing. And like I said before, one can think of consciousness as being really elementary in the sense that every particle interaction entails a little blip of consciousness. And so our consciousness then is constituted out of a huge number of these little primitive blips, so to speak, and in a hierarchy of larger and larger structures. Now, ultimately, all these structures are inside certain geometrical algebraic structures of the kind that I described. And I might add that these structures are very, very closely, intimately related to some of the more recent ideas in physics, which is superstring theory. And this, I mentioned that in some detail in the paper, but I go into much more detail in my book, ADEX Theory.
Thank you once again for your time, because this is a fascinating conversation.